Presented by Caltech.
I am very pleased to introduce our speaker for this evening's Watson Lecture, Bren, Professor of Medical Engineering and Electrical Engineering, Dr. Lihong Wang. Professor Wang received his bachelor's and master's degrees in optics from the Huazhong University of Science and Technology in China and a PhD in electrical engineering from Rice University in 1991. Before joining Caltech, he was on the faculty of the Department of Biomedical Engineering at the Washington University, St. Louis. He joined Caltech in 2017 and is the founder of the Caltech Optical Imaging Laboratory in the Andrew and Peggy Chung Department of Medical Engineering. A prolific inventor, scientist, engineer, and innovator, Professor Wang pioneered the field of three-dimensional photoacoustic tomography, which has revolutionized biomedical imaging. This imaging technology, which provides unprecedented molecular, metabolic, and functional multi-scale in vivo imaging of structures ranging from organelles to human organs. Biomedical applications of his new imaging techniques include imaging of cell nuclei, gene expressions, angiogenesis, metabolism, ocular disease, breast cancer, melanoma, colon cancer, prostate cancer, and brain function. Professor Wang's numerous patents and inventions form the technical basis for two companies that are commercializing photoacoustic tomography. Professor Wang is also the inventor of the world's fastest camera, capable of taking 10 trillion frames per second. Professor Wang has received numerous awards and honors for his research. He is a recipient of the NIH Director's Pioneer and Transformative Research Awards. He also received the OSA Mies Medal, IEEE Biomedical Engineering Award, and the SPIE Britton Chance Biomedical Optics Award. Professor Wang was conferred an honorary doctorate by the Lund University in Sweden. His book entitled Biomedical Optics, Principles and Imaging, one of the first textbooks in this field, won the 2010 Joseph Goodman Book Writing Award. Professor Wang is an elected fellow of numerous professional societies, including the American Institute of Medical and Biological Engineering, IEEE, Optical Society of America, and SPIE. Earlier this year, he was elected a member of the National Academy of Engineering in recognition of his inventions in photoacoustic microscopy, enabling biomedical applications. Ladies and gentlemen, please join me in welcoming Professor Lihong Wang to deliver the Watson Lecture.
Thank you, Ravi, for the very kind introduction. Thank you all for coming here. I'll be talking about two of the technologies my lab has been working on, photoacoustic tomography and compressed ultrafast photography. The first technology focuses on deepening the penetration in scattered materials or opaque materials such as biological tissue. And the second one focuses on imaging. We want to beat light propagation. We want to image as fast as light propagates. But we face daunting challenges. First of all, many materials in the world are opaque or scattering. We often call them turbid materials. If you look at this photograph, apart from the air and water, everything else is turbid. You look at wood, snow. Now, if you zoom into this person, except the eye, everything else is turbid. The biological tissues tend to be very turbid, very scattering. We can't even see through our own palm. So to understand the universe better, to conquer cancer, brain disorders, we really have to figure out a way to overcome turbidity. Another grand challenge we face is that light propagates too fast. We know that nothing else propagates faster than light. Light propagates at the ultimate speed, if Einstein is still correct. So to image sound, which propagates 5 orders of magnitude slower than light, we can use light, because light propagates faster. But to image light, what do you use? You have to use light itself, because there's nothing else propagating faster. And so we face a problem. As we all know that when an object propagates sonically or supersonically, you will hear this sonic boom, or you will see this supersonic Mach cone. And there's an optical counterpart or photonic counterpart. And if a charged particle propagates in a material at a speed greater than the speed of light in the material, you would expect to see a Mach cone as well, but that's a photonic Mach cone. But because light propagates so fast, the current technology can only see something like this. You will see light, that's it, but you don't see a cone. And so we're going to fix this problem. There are a lot of reasons for the type of researches we do, but to be more specific, we're going to focus on biomedical research, biomedical applications. From the physics perspective, light-matter interaction occurs at the molecular level. This is very important. You look at the entire EM spectrum and plotting in wavelength. This is many orders of magnitude, typically at least 24 orders of magnitude in terms of wavelength or photon energy distribution. But light occupies this tiny region. This is so special because this is the only region where EM wave matter interaction occurs at the molecular level. Given the fundamental role of molecules in biomedicine, we really have to work on this problem. We have to figure out a way to work on imaging so we can probe molecules or we can address molecules for different applications. In fact, by detecting molecules, we can provide in vivo functional imaging, very much similar to functional MRI. In vivo metabolic imaging is similar to positron emission tomography. In vivo molecular imaging of gene expressions or disease markers. Even in vivo label-free histologic imaging of cancer without tissue excision. And you can see this set of powerful capabilities. But again, we face the challenge that tissue is so turbid. Now, if you inject a photon packet into a piece of tissue and plotting only the top 2 millimeters, pretty much like the skin thickness, and you will see how photons propagate. Within the first 1 millimeter or so, the photon packet can propagate as a group. This is so-called ballistic or quasi-ballistic regime because the photons haven't gone through enough scattering events. And so they travel together. And that's a regime where we can image optically quite easily. But beyond about a millimeter, the photon propagation is like a random walk. So the next lecture will be on random walk. You should come as well. And this is actually random walk. As we know that's the basis of basis of diffusion. It doesn't matter whether you're talking about photon diffusion, heat diffusion, or chemical diffusion. I'm sure folks coming from different backgrounds have learned the same equation, but they have different physical meanings. And we're talking about photon diffusion here. That presents a big challenge for deep penetration in scattered biological tissue. If we look at the history of optical imaging, at least about 350 years ago, we started with conventional optical microscopy. That was a great invention. It allowed us to see tiny structures, subcellular structures even. But the penetration is limited to 100 microns, which is called aberration limit because the conventional microscopy depends on perfect photons. Photons that have perfect wavefront. They have not gone through any aberration. That type of photons actually attenuate very fast beyond 100 microns. You don't really have any. Since the invention of the laser, that was only about a half a century ago, we're now able to provide the penetration 10 times deeper. Now we're talking about 1 millimeter penetration because using lasers' properties, we found out ways to reject all those so-called bad photons, photons that have been multiply scattered or diffused, but we try to retain the ballistic or quasi-ballistic well-behaving photons for imaging information. And that worked out great. But those type of photons will disappear beyond about a millimeter. So there's not enough to use beyond about a millimeter. That's called the optical diffusion limit. what else can we do to go beyond this limit? We actually embrace all photons. Let's say there are no bad photons. We're going to use the bad photons for deep penetration, because if you can tolerate scattering, light can go quite deep, especially at the right wavelength. I'll give you more results later. And so now photoacoustic tomography uses all those photons that have gone through random walks. They're diffuse photons. Then we convert them into acoustic energy. So we're going to detect ultrasound for image resolution. All of a sudden, we overcome the optical diffusion limit. We enhance the image penetration by nearly 2 orders of magnitude. Now, we're not just talking about multiple millimeters, but we're talking about multiple centimeters of penetration in biological tissue. Like anything else, we face the next challenge, something I call the optical dissipation limit. The big question is, can we find ways to overcome the next limit? And there's this active field, which is extremely exciting, but equally challenging. It's called wavefront engineering, or time reversal. I don't really have a lot of time to talk about that today, so I'll just leave it at that. And there's a hope that we can actually corral photons at a given depth. There are a lot of photons, they're just scattered all over the place. The big question is, can we actually corral photons to generate hotspots? If you can do that, then you can provide imaging or therapy. You can do a number of things with that kind of hotspots. So today I'll focus on photoacoustic tomography on that chart. There are 2 major incarnations of photoacoustic tomography. The first one is photoacoustic computed tomography. Photoacoustics was first reported by Alexander Graham Bell. That was 1880. He had this idea of photophone as opposed to telephone. Of course, photophone never went anywhere. So because you'll see the reason it requires line of sight propagation. So his idea was to encode sound into a light beam. He actually used sunlight to do the experiment. And the sunlight was propagated in space, convert back into sound again. And it was phenomenal. So, but in his days, there was no concept of laser, ultrasonics, tomography, or computer. Now we have this set of powerful tools. We want to combine that with this old physics to create a new imaging modality, photoacoustic tomography. In photoacoustic computed tomography, we start with a very short laser pulse, typically nanosecond laser pulse. We broaden the laser beam such that the energy per area is very safe. And so there's ANSI safety limit we have to follow. And they don't regulate the total energy, but they regulate the energy per area. If you think about the physics behind it, that's really what matters in terms of causing damage. So you want to avoid causing damage. We allow photons to scatter. When light gets absorbed, they will generate very rapid heating. Every millidegree gives you 800 pascals of pressure, which is detectable already. But if you heat up hundreds of milledegrees, you're still within the safety limit, but you can generate a very good signal-to-noise ratio to work with. We deploy ultrasound transducers outside the tissue to detect ultrasonic waves generated by the laser light. Notice here the acoustic scattering strength or acoustic scattering coefficient is orders of magnitude weaker than optical scattering. In other words, biological tissue to ultrasound is very much like a bottle of water to light. So sound can really see tissue very, very well. But here, we're combining optical contrast with ultrasonic resolution in a single modality. So if you were to use sound only, you can fire a sound pulse into tissue, you can listen to the echo, but you're not going to get any of the molecular specificity. You're not going to see molecules. You're not going to see any color. You're going to see mechanical properties. So ultrasound imaging detects acoustic impedance mismatch, but we're detecting molecular information. We can tell arteries apart from veins, for example. So once you have all the signals, we have to run image reconstruction. I don't want to get into the details of the math. There's something called the inverse Fourier read-on transformation, and that you have to run on a computer to form an image. But I can give you a very simplified analogy to show the principle behind this reasonably complex image reconstruction. Let's say we have a thunderbolt. The minute you see the lightning, you can reset your stopwatch. When you hear the thunder, you can record a time delay, T1. Multiply T1 by the speed of sound in air, you would define a radius for the spherical shell on which lightning took place. If you have 3 such measurements centered at different locations, you can triangulate. This is actually somewhat similar to LIGO, if you think about it, except they deal with a tougher situation because they don't know time zero, we do. So that complex algorithm is actually based on this very simple analogy. In 2003, we reported the first functional photoacoustic tomographic images, also the first in vivo images. Without removing the skin or skull, and we have a small animal, rodent, and light can go through the skin skull to penetrate into the brain cortex. We can detect brain function. You can see this one-sided signal. So we wiggled one side of the whiskers of a small animal. The contralateral side of the brain was hemodynamically activated. And so this is called functional brain imaging. This paper now is the most cited in the field of photoacoustics. You can see the growth of our field since 2003. The field has gone through this exponential growth. Since 2010, the Conference on Photoacoustics has become the largest at a 20,000 attendee Photonics West, which is the largest optics gathering. So you can ask, why is photoacoustic tomography so exciting? I'm plotting imaging depth versus spatial resolution. This is the only modality that provides omniscale in vivo imaging with consistent contrast. So we're imaging light absorption as the contrast mechanism. This is very different from fluorescence imaging, for example, because any molecules absorb light. So as long as you can find the laser wavelength tuned toward the absorption peak, you can detect, in theory, any molecules. This is extremely powerful in terms of the versatility. Each horizontal bar represents one of the systems we built in our lab. We actually have far more than I can plot here. And you can see how we can scale. This dashed line roughly connects all the different implementations. No matter what depth scale you're working at, you can count on roughly 200 pixels in the depth direction. So it'll give you enough definition to figure out the structures in the tissue. Now, if you look at the current practice, for cells and below, we prefer to use optical microscopy, so we're detecting optical contrast. For tissues and above, because standard optical imaging doesn't give you the right penetration, we switch to non-optics. We're going to use MRI, ultrasound, what have you. There's a big divide between the cell and tissue levels. Photoacoustic tomography bridges this gap and provides a continuum from organelles all the way to small animal organisms. So this type of capability will be very useful because now we can correlate information acquired across all relevant length scales. Applications include omniscale biological research from organelles to small animal organisms, translation of microscopic lab discoveries to macroscopic clinical practice. We don't translate enough. We have a lot of exciting microscopic lab discoveries, but we need to translate them into clinical use. For the 2003 work, we used a single element transducer. We had to rotate around the animal, which took more than 20 minutes to acquire data set for a 2D cross-sectional image. Now we built a dream machine with a single laser shot. We can generate a 2D image. The data was acquired within tens of microseconds. The system can be used for trunk imaging of a small animal. We start with the right laser. We send it through a conical lens to convert the beam into a hollow cone beam. We brought the beam back to the animal trunk to focus it so we don't waste any energy of the laser beam. We use a full ring ultrasonic transducer. I'm only plotting half of the ring, so we're viewing the animal over 360 degrees. That gives you the best quality image. We follow the Nyquist sampling principle, as we learned that maybe oftentimes in the time domain, so you want to sample at least 2 points per period. Now, we're talking about the spatial domain, so we need to sample at least 2 points per wavelength. Otherwise, you may see some artifacts. And we use a preamplifier to amplify the signals to maintain the signal-to-noise ratio, because our signals is roughly order of magnitude weaker than standard pulse cycle ultrasound return signals. And so we would really want to retain the high SNR in the very beginning. If you wait a little bit, you propagate a signal over cable, the cable will pick up noise. And then you have low SNR, it'll be really hard to boost up the SNR, as we know that. The amplifier will amplify the signal and noise together. It will not amplify the SNR, unless you pay a price in terms of bandwidth. We have a one-to-one data acquisition. So we have an equal number of data acquisition channels. That means with a single laser shot, we get all the data acquired. The data time depends on the field of view. So basically the diameter of the field of view divided by the speed of sound. Typically it's within tens of microseconds. That's how fast we can form a 2D cross-sectional image. Then we use the computer to run the image reconstruction to form an image. Here's a close-up of the key system, key components. You have a hollow beam, and then we use ultrasonic focus to provide elevation or vertical resolution. The XY resolution comes from the image reconstruction. The system can also be used for brain imaging. Here we use a diffuser to generate a solid cone beam as opposed to a hollow one. And once you shine the beam onto the small animal brain, you will generate photoacoustic signals. The rest of the systems will be the same. Just to give you an example, and this is a picture of a small animal. This red line shows the current cross-section being scanned, and you can see the image right here. Again, each slice was acquired within a single laser shot, and you can see this close-up here as well. And as we scan, we're repeating the laser pulse at 50 hertz. So each second, we generate 50 frames. And you see the kidney area, you see the symmetry of the two kidneys. So this type of capabilities will be very useful for the pharma. We're working actually with a pharmaceutical company for applications. This is another example. And for this particular set of images, we park the system at a given location. Here it's near the liver. And so we watched animal breathing. Imagine you want to discover a new drug. You want to monitor the same animal over several months. If you were to use X-ray CT to acquire images, the radiation dose sometimes kills the animal. So the accumulation of the radiation dose is simply too much. And even then, you may not have the right contrast to see the tumor. And we want to see how the tumor shrinks with a given drug. So we can use our technology without injecting any contrast agents. This is entirely safe because we're using non-laser radiation, and that's not going to cause any optical damage. The sound that's produced by the laser absorption is so weak, we don't have to worry about any ultrasound damage. So there's no damage to the animal at all. This is entirely safe. We were so excited about the small animal data set, we decided to scale up the system for human breast imaging. You see this bed right here with an aperture. So this aperture has 22 centimeters diameter, which is big enough to accommodate most breasts. This system operates around this point, multiple centimeters penetration, hundreds of microns resolution. From a healthy volunteer, we acquired this in vivo image. We use color to represent the depth from the very surface to about 4 centimeters, which is already the chest wall. You can see this nipple region. Each slice was acquired with a single laser shot, and because this is a bigger field of view, so the data acquisition took a little longer, which is about 150 microseconds or so. Still extremely fast. So there's no breathing artifact. There's even no heartbeat artifact to worry about. To minimize breathing artifact, we asked the patient to hold her breath. Within 15 seconds, we acquired the entire image of the whole breast. And so this is a synthetic 3D image with color showing you the depth. The smallest vessels we see here is roughly 1/4 of a millimeter in diameter. This is extremely small. Now, the other alternative to see vessels this size or even close to this size is MRI. With plain MRI, you can't really see vessels this size. You may be able to see vessels of the first order, the largest blood vessels. But to see smaller vessels, you have to inject gadolinium, which is a heavy metal. As we know that, there are side effects associated with gadolinium. Even then, the smallest vessels detectable was roughly 1 millimeter in diameter. So we have 4 times finer resolution or sensitivity in terms of vessel detection. Yet we don't inject any contrast agents. Just to give you an idea about different slices, we're showing you some representative images from 0.5 centimeters all the way to 4 centimeters. You can see how well we can detect blood vessels. Let me transition to photoacoustic microscopy. So for here, we use a different detection technique. Let's assume there's a piece of tissue and there's a light absorber inside. We fire a light pulse to generate a photoacoustic wave. Then we use a focused ultrasound transducer to receive the photoacoustic signal. Because of focusing, we can generate XY resolution, but the time of arrival of the signal will give you Z resolution. So what we detect is a time trace like this. This absorber will become a spike. And usually the surface has some signals as well because of the stronger light. So this is a 1D image. We call that A scan or A line. If you scan across the tissue, you would generate a 2D image or a B scan. If you raster scan on the surface, you will get a 3D image. Here, the resolution comes from the ultrasound altogether in both X, Y, and Z directions. And because the optical beam is often much broader than the acoustic focal point. So that means the XY resolution comes from the acoustic focus. So we call this version acoustic resolution photoacoustic microscopy. This photograph shows the first 3D photoacoustic microscope. I will not get into the details, but show you the key components instead. So we start with a hollow beam. We refocus the hollow beam into the tissue. On the tissue surface, we have this donut beam. So we made this beam dark colored, so the center of the beam is made dark just to minimize the surface interference. The ultrasound detection is confocal with light illumination just to maximize the signal-to-noise ratio. Again, with a single laser shot, you get a 1D depth resolved image. This head is raster scan in a water tray. There's a membrane window here that's used to couple light and sound. The object we want to image is placed below the membrane window. This is the map bridge around this point. I just jumped from here to here. It gives us about 3 millimeters of penetration, but tens of microns resolution. You can get an image of the skin like this. This is our own palm. We can see blood vessels. If you were to use X-ray to see blood vessels, you have to inject heavy metal, like typically iodine, to enhance the contrast. Even then, you don't see small vessels like this. You get a B scan or depth resolved image that shows some of the standard skin structures. You can also push the resolution even further to refine the resolution at the expense of penetration. So you can push it to about 1 millimeter of penetration, but single-digit micron resolution. If you do that, you will get images like this. So within 1 second, we get a 3D image of the brain cortex of a small animal, and we actually use the color to represent a physiological function called oxygen saturation. As we know, that's very important for oxygen delivery in our body. And you can see the different colors showing you different oxygen saturation. As we know that you might have used this before in a clinic, right? Physicians nowadays sometimes clip a little gadget at your fingertip. It's called pulse oximeter. And that detects oxygen saturation, but only in veins, only in arteries, but not veins. So we actually detect both arteries and veins. We give you vessel by vessel resolution as well. And we can also use to detect brain activation, as you can see right here. If you do one-sided stimulation, you can see the brain activate accordingly. We can even refine the resolution further, down to something called super resolution imaging. As we know that whenever you use a wave, the standard best resolution is wavelength over 2, lambda over 2. That's the best resolution. Now, if you can beat that, it's called super resolution. So by using nonlinearity, we can actually beat that lambda over 2 resolution. 234 is our wavelength over 2 resolution, and we see mitochondrion, which is a subcellular organelle. But using nonlinear photoacoustics, we get 90 nanometer resolution. Now we can see some of the inner structures of a mitochondrion. That's a comparison toggle between the two images, and that's an EM micrograph for comparison. Now we're at this point. So I described different representative capabilities all the way from here now, transition into here at the organelle level. I don't even believe we're at the limit. Now let me switch to compressed ultrafast photography. The first generation of our technology gives us 100 billion frames per second. And we had to slow down the movies 10 billion times. You probably realize this already. You're watching the slowest slow motion movies. And so at this speed, 100 billion frames per second, we can watch the fastest phenomenon in the universe, light propagation. We fire a single light pulse, laser pulse. We can watch how the pulse propagates, reflects, refracts, and we actually send 2 laser pulses here into 2 different materials and watch how they have a race. And now we can change our camera to color version, and this is a 2-color version of our camera. And one channel detects green light, you'll see that. That's the excitation. And then we use red to indicate fluorescence. So this is a single laser shot fluorescent light. And you just saw the green pulse, that's excitation. The fluorescence takes about nanoseconds to relax, but we have picosecond type of resolution, so that's why the fluorescence feels like forever. By the way, this is very different from what you might have watched before. If you might have watched a very fast action type of movie, but that may have been acquired repetitively by firing the laser pulse. Then you get snapshots with different time delays. Then you have to synthesize all those snapshots into a movie. Here it's a single shot. In other words, we fire the laser pulse only once. We watch the entire event in real time with a single pulse. So to explain how the system works, I have to come back to a standard street camera. We start with this slit because we have to reserve the white dimension for temporal resolution. The slit is mapped onto this photocathode. We convert photons into electrons, but we have an accelerating electrode that will pull the electrons forward. When the electrons pass through this pair of electrodes, we apply a voltage ramp. This ramp is very steep. Depending on the time of arrival of the electrons will experience different deflections. In other words, we now have converted time into Y position. And in a way, this technology has a frozen time for us because now you don't have to worry about a fast detector. You can use a slow detector just to detect a Y distribution because the Y can be converted back into time t. Now, in the end, we magnify the signal, we convert electrons back into photons, then we can use a standard CCD or CMOS camera to detect the signal at the back end. This has been around for decades. It gives you really fast imaging, but only 1D information, only X, but not Y. So to get a 2D movie, you have to scan. This is an example. You get one fast movie along this line, then you have to scan to get a 2D movie. And so you have to repeat the event. The event has to be highly repeatable, and it's really not real time. So we want to do something better. We start, let's say, with the object, arbitrary object. Let's say the intensity distribution is versus x, y, and time t. Before we send it to the street camera, we send it to a digital micromirror device with a pseudo-random pattern written on the device. We denote that by c of x, y. I will be multiplied by c, then we route this encoded pattern to the street camera. We also use the street camera very differently. We're going to open up the slit as widely as possible. We'll convert photons into electrons. They will go through this shearing because of the voltage ramp. Then in the end, we'll integrate using a CCD camera, so the integration time is over the exposure time of each frame. In the end, you get this equation. So I multiplied by c by s by the time integration t. In the end, you get an energy matrix E versus xy. All we have to do is to solve this equation. Now, if you look at this equation a bit closer, you see a problem. On the left-hand side, we have 2 dimensions, x, y. On the right-hand side, we have 3 dimensions, x, y, and time t. Whenever you have an extra dimension, oftentimes you have more variabilities. In other words, you you have more unknowns than you have measurements. We got a problem. As we learned in middle school, you should have as many measurements at least as you have unknowns in order to solve the equations. All right, our middle school teachers are still correct, but we're going to prove them wrong as well in a way. But it turned out if I is compressible, in other words, if the movie is compressible in the original scene, you can actually solve this equation. And so why is that so? If I take a still shot, a still photograph, use our smartphone, we can compress that image. If you take a movie, you can compress even more because adjacent frames tend to be highly correlated. So it turned out in most cases, this eye is highly compressible. So the true number of unknowns is far smaller, far less. As a result, we can actually solve this equation. And we use this relatively new theory called compressed sensing theory. And that allowed us to solve this equation to come up with a movie like this. Recently, we enhanced the speed even further. Now we've changed from 100 billion to 10 trillion frames per second. That's another factor of 100 enhancement. And you see the two generations. And this first one shows you at 100 gigahertz, you see a movie. We show the scale bar here at 10 millimeters, but this one is much finer, 10 times finer scale. And also we see more frames. So in this particular example, we show light transmission through a piece of glass. You see the light pulse gets reflected at the first interface. Then it'll disappear for a minute because the glass is so transparent, it doesn't scatter any light toward our camera, so the light becomes invisible. But if you wait, it'll come out the other side. So I had introduced our technologies as fast as possible, but I like to talk about some potential applications and some of the remaining challenges we have. For photoacoustic tomography, it's very natural. Now, I showed you an image of a normal, healthy patient, but we really want to detect breast cancer. And give you one example. This is a 69-year-old breast cancer patient. In fact, X-ray mammography missed the tumor. As we know that, X-ray mammography is not perfect. First of all, it has tremendous problems for young women's breasts because they're radiographically dense. But even for this 69-year-old woman, we have a problem. And you see a little dot right here? That's a piece of metal. So ultrasound turned out to be able to detect this breast tumor. We label the breast tumor on the skin surface with the metal target, and then we use X-ray to take an image of the breast again. Using our technology, first of all, just to orient yourself, this is the nipple region. But we see a very high density area, as you see right here. This is a density plot of blood vessels. And we can see the tumor really well, presumably due to angiogenesis, because the tumors are aggressive, they tend to grow new blood vessels. We can also use elastography to look at stiffness of the tumor. And we allow patients to breathe normally after we acquire the 3D image, so we focus at the tumor plane. And by tracking the motion, we figure out the strain or the areal change, and you can see the tumor region has much less change relative to the surrounding region. So there are two contrasts for now. We can even add additional contrast mechanisms, and that would increase the detection accuracy. So far, I've been talking about mostly blood or hemoglobin detection. But as I mentioned earlier, we should be versatile enough to detect other molecules. As an example, we're going to detect melanin, as we know that the skin has a lot of melanin. And melanoma has melanin. So it's natural to target melanoma. This is a melanoma. We can take a photograph. You see the surface, but you don't really see how deep. But the depth is really critical for melanoma detection and staging, even for surgical planning. We started by using ultrasound. The ultrasound doesn't really see the melanoma. Then using our technique, we see a beautiful profile, a 3D profile actually of the melanoma. You can overlay that to the ultrasound image, and you can generate the depth. We can report the depth in real time. This one happens to be 1.9 millimeters. The standard clinical practice is to cut a slice out of this melanoma based on the surface look. And depending on where you cut, you get different depth, something called Breslow's depth. And that's a standard number you report, and that's used to stage the patient. And so the breast lobe depth for this patient is 1.6 millimeters. It's actually smaller. And that's sort of expected because the histology preparation causes shrinkage. In fact, so our in vivo number is much more accurate than the ex vivo number. We decided to move this technology even further. We know that the primary cancer doesn't really kill people. Most cancer-related death is due to metastasis. That means the primary tumor has migrated mainly through the blood vessels to a remote organ. They just replant it, they generate new tumors, and that becomes a huge issue. So if we can find a way to curb metastasis, we can potentially save a lot of lives. And we decided to detect something called CTC, circulating tumor cells. So we decided to start with the melanoma CTCs because they have natural melanin. We don't even have to label the cells, and they should be detectable. We can optimize our laser wavelengths so the melanoma really stands out from the rest of the blood. We detect ourselves. In normal situations, we don't detect any bright spots. Then we took the system to melanoma patients. The patients were given to us without prior knowledge whether they have any CTCs because the standard practice doesn't really detect them. And so we knew these were melanoma patients. Their primary tumors had been removed before we imaged them. So in a few of the patients we imaged, we actually found circulating tumor cells. In this case, you'll see this single CTC crossing the field of view. And for the same patient, ironically, you'll see a little doublet. So the two of them travel together as a group. The standard practice, if you want to detect any circulating tumor cells, is to draw blood. You would draw 7 cc out of 5,000 cc of our whole body's blood. So that 7 cc may miss the tumor. And we can already detect a volume far bigger than 7 cc. Our ultimate goal is to detect the entire 5,000 cc of blood, maybe even multiple rounds. So we can provide the ultimate sensitivity of melanoma CTCs. And there's even something further we're trying to explore. The minute we detect a CTC, we can follow up in real time and fire a stronger laser pulse to damage the CTC, damage the cancer cell. And we can control the laser intensity without causing damage to the blood, to primary red blood cells. So the blood stays safe, but we burst the CTC. And we can even use a short enough laser pulse. So we burst the melanosomes, which is melanin-containing package, but without causing damage to the antigens. So the big question we have remaining to answer is, can we actually activate the immune response by releasing the antigens? I talked about oximetry, and I showed you images showing single blood vessel level oxygen detection, oxygen saturation. Can we push it to the ultimate level, single red blood cell level? And this is our system at 1 hertz, 20 hertz. We operate our system at 200 hertz. And so as a result, you can get a movie like this. We can watch how red blood cells bifurcate in real time, in vivo. And you see it's not totally random. They actually tend to group depending on the need of oxygen. Then we imaged our own finger cuticles. This is human image. We use 2 laser pulses of different colors, so we can actually see the color of red blood cells. This is pseudocolor representing oxygen saturation. If you single out one of the red blood cells, you see the color change because oxygen is released. Because there are 2 forms of hemoglobin, oxy and deoxyhemoglobin. They have different colors, and we can quantify the ratio between the 2. And that tells you how much oxygen is released. Our hope is to provide a fundamental tool to physiologists to understand at the most fundamental level how oxygen is delivered to the capillary, at the capillary level. We all know that physicians have 2 eyes, radiology and pathology, or histology. Imaging is radiology, so we are actually part of that. We provide imaging. But we also want to be part of the histology. We want to do better, because the current histology is invasive. The minute the physician tells you, we want to do histology on you, that means they're going to cut tissue. They're going to go through a lengthy procedure, not real time, to prepare the specimens before they can report the results to you. And so there's this big problem for lumpectomy surgery. 1/3 of the patients roughly will come back for a second surgery because we don't remove the tumors altogether. We leave some residuals behind. Can we actually develop a much better technology that's real-time, that's intraoperative? We can tell the surgeons where to cut. And so we're moving in that direction. We can provide something called label-free histology. So we don't have to label, we don't have to process. Give me a piece of tissue, we can image it right there on the spot. And our ultimate goal is to provide an in vivo version of that. We just have a wand that can tell you if that region is cancerous or not. But to begin with, this is what we have. This is a piece of tissue from a human breast cancer patient. The pathologist can tell the tumor from the normal region already using our image. And you can see these are close-ups of the normal and the tumor region. The same piece of tissue was processed using standard histology that requires staining or labeling using two types of dyes. You can see how well they correlate. And so we're moving this into clinical application as we speak. So far, all the contrasts have been endogenous. We can also image exogenous, something you inject into the body. And we know that breast cancer staging right now is a surgical procedure. We want to convert that into a needle biopsy. And what we do is we inject FDA-approved dye into the breast. The dye will be accumulated by the lymphatic system at a central lymph node, the first draining node. And we can image the draining node. And then we can guide the needle to take cells out, and then we can tell if the cells are cancerous. And we've imaged this in real patients. You can see here, this is a central lymph node, and the color is due to the dye accumulation. And we can see the needle here as well. The ultimate challenge, in my opinion, for photoacoustic tomography is adult human brain imaging, because the skull is in the way. The skull is quite thick. For some animals, that's not quite an issue. But we're pushing that direction anyway. So this is an MRI image of a human volunteer. And this is the volunteer in our imaging system. And we got some very encouraging images already. As you can tell right here, we can see the blood vessels. The remaining challenge is how do we tease out the weaker signals from the brain cortex, from the superficial skin vessels. And most of the big vessels, the strong vessels, are from the superficial layers. And so that's a work in progress. Let me talk about the cameras. I mentioned earlier, for that Cherenkov radiation, where that's something called superluminal phenomenon, we couldn't see the cone. Where's the cone? So just to give you a reference, this is the sonic boom, and which shows this supersonic Mach cone. And we created a superluminal situation as shown right here that can actually give you a cone. This is a photonic Mach cone. This is real time without any repetition. We just fire a single laser pulse through a channel, and we have a background medium that slows down light, and that create a superluminal situation because the source actually propagates faster than the rest of the material, the light in the rest of the material. And this type of phenomenon has been used for medical imaging, for dose control. So this is quite useful in medicine. We're thinking of using the camera for some fundamental physics. Optical chaos is a very interesting physical phenomenon, but so far there's no experimental technique that's fast enough for people to observe the phenomenon in real time. But for the first time, we were able to do that. And so we created this sort of like a half mushroom type of cavity. We inject a very short light pulse. You know, this white ball is not a ping pong ball. It's actually a light pulse. And it's bouncing around within this cavity. We had 2 takes. Initially, they look the same. But if you watch long enough, they will deviate. And we actually overlaid these 2 movies, as you can see right here. You can see at some point, they will deviate, they'll split. Here, we have another gated cavity, and they were trapped in this rectangular shaped cavity first. But this arm is a gate that's being gated at the light speed as well. And when you open up the gate, the light pulse can cross, and in fact, it'll come back again when we seal the gate. There are also some more mundane applications. I'm sure you've heard of sonar or LiDAR. And standard LiDAR means you have to have some sort of scanning because they don't really have the spatial and temporal resolution simultaneously, but our CUP, or compressed ultrafast camera, has both spatial and temporal resolution. So we can do a single shot LiDAR. And this is a LiDAR experiment. We have this swimming fish in a water tank, and we can show you the depth. We use color to show you the depth, and you can see this live fish swimming here. You can track the trajectory as well. We can even go through turbidity. So like fog, biological tissue, this, you can imagine maybe one day we can use this technology for autonomous cars where you can provide an image of the road even in a foggy situation. And let's say this is a scatter medium that's similar to fog, and you place your camera right here. And if you have something moving behind the scene, here we actually assume there's a little airplane flying behind the cloud. In a lab situation, of course, you can see this plane behind the scatter medium. The biological application we're after is to see action potential propagation. We know that the neural network is a very complex system. There are technologies that allows us to get an ex vivo image of the neural network. We can get a map of the neural network. And that's like a road map. However, we don't see live traffic. We want to see live traffic. When there's action potential propagating over the network, can we capture that event? And so this is a work in progress. This is a computer simulated situation that shows that with a standard camera at 2 Hertz, you're not fast enough to see the action potential propagation. By using our camera, in fact, we have to slow down to roughly 1 megahertz, and we can resolve the action potential propagation. So this is one of the dreams we're working on right now. I have to disclose my financial interest in 2 companies that have commercialized our technologies. I want to thank NIH, March of Dimes, and NASA, or TRISH, for funding our research. For more information, please visit our website. We have a couple books for more details. I also want to say I'm very grateful to Caltech. Caltech's built me a dream lab, as you can see right here. That's pretty much the entire basement floor of Keck building, plus part of the sub-basement. And so this is the only omniscale imaging lab in the world that provides you organelle level imaging at the near end, all the way to macroscopic whole organism imaging at the far end. So we're poised to work with some biologists and physicians to conquer some of the big problems. Credit goes to my lab members. There are a couple of photos here. Actually, some of my lab members are here in the audience. Would you all stand up so that you can be recognized later on? Maybe our audience has questions to ask you. Our lab members have done all the hard work. We have more openings for the next generation of students and postdocs. Please feel free to recommend them to me if you see interested candidates. Thank you very much for your attention.